Okay, now that we know a little bit about phase diagrams, let's delve into phase thermodynamics, the thermodynamics of phase transitions. First, let's talk a little more about the chemical potential mu. I want to show you that, in fact, similar to what we have for G, how G varies with temperature and pressure, we can write an equation for mu where instead of just entropy and volume, when we have for G, free energy, we instead have partial molar entropy and partial molar volume. So let's start out. Mu is a function of temperature and pressure. Note that we have the number of moles not in here because it's the partial molar quantity. We've taken care of that. So like we've done for free energy and Helmholtz free energy and all those other things, we say that d mu will be how mu changes with temperature at constant pressure times dP plus how mu changes with pressure at constant temperature times dP. Remember that mu, I just write mu, was how G changes with number of moles at constant temperature and pressure. So let's go ahead and put that in here. So now we have d mu is how G changes the number of moles at constant temperature and pressure, how that quantity changes with temperature at constant pressure, plus, we'll substitute that in there, how G changes with N at constant temperature and pressure, and how that quantity changes with pressure at constant temperature. There should be a plus sign there. Look at this. This is G. We're taking the derivative first with N and then with T. But G is a state function, so it doesn't matter whether we take it first with N and then T or with T and N. And the same way over here. So we can rewrite this equation as how G changes with temperature at constant pressure, number of moles, and then how that changes with N at constant temperature and pressure, plus the derivative with respect to N of how G changes with pressure at constant temperature, then how that changes with N at constant temperature and pressure. And this would be a dP here, a dt, and this would be a dP. So we just switch the order of integration. Now, how G changes with temperature, constant pressure, remember from a previous lecture, that's minus the entropy. And how G changes with pressure at constant temperature, this is equal to volume. So we can rewrite this as how minus S changes with the number of moles N at constant temperature and pressure times dt, plus how volume changes with number of moles at constant temperature and pressure times dP. This we define, remember, as minus the partial molar entropy. So when you take a quantity and take the derivative with respect to number of moles, you get a partial molar quantity, and we'll denote the partial molar quantity with a bar above the quantity. And this you might also recognize as the partial molar volume. So we can rewrite this as minus S dt with partial molar plus V dP with partial molar. If we contrast and compare what we did for delta G, remember delta G is minus S dt plus V dP. So it's very similar, except that instead of entropy and volume, you have partial molar entropy and partial molar volume. So how chemical potential varies with temperature is minus the partial molar entropy. Same way with how chemical potential changes with pressure.